We would have started today, but then
We were going to start on the first.
Well, you can't. You literally can't. The features and answers can't do all the things you need for the project.
Oh, well, I was here over break.
Oh, well, then that's different. But, like, and that's something that bothered me. When he said, oh, you had 12 days to do the homework. 12 days, if you were here throughout break and had access to the full version of answers. If you left campus and didn't have access to the full version of answers, the security version cannot solve those problems. Really could not work on it until you got back to campus. So you had up to 12 days. You didn't really have 12 days. It's just. And we were going to meet today to do. So you're starting on the project tomorrow, the storage project. Yeah, we were going to start today, but one of my group members just said they can't meet. So.
No, sorry.
Okay.
Yeah, projects in this, and I have the dynamics project.
You need a personal thing, right?
Yeah.
Okay, Caleb is online. Can you hear me?
Loud and clear. I got you.
Okay, thank you.
Oh, towards
Yeah.
Okay, so let's just take in-class attendance. Yeah, don't worry about paper. It's like I don't know you, right? I don't need that. Don't worry.
Yeah, you said don't. Okay, yeah, you don't know my name. You don't know me? So should we put it up there?
Okay.
I'm not we can't start till tomorrow. We still lost no idea what we're doing. Because we asked him questions and so many things. It's like, just figure it out with your group.
Yeah.
And it's like,
And then he's like, you don't have issues, ask questions.
it's like when we ask you questions. That's what I've noticed on the homework. It's like, he's like, if you have questions on the homework, email me. But when I email him questions on the homework, his response is usually just telling me to look at Canvas without actually helping me. It's like, oh, just look at what I posted on Canvas.
So
Like,
I hope you are enjoying the end of the semester week.
No.
Lots of things all of a sudden starts to happen. And then I guess the best way to stay survival is be healthy. Don't stay up all night and stuff. Well, sleep, you know.
I went to bed at 3 in the morning.
And then sleep and eat, do things. It's like you get light. You know, when I was a student, I didn't need to sleep. Nowadays, I have to sleep 10 hours, otherwise I feel like I'm dead. Anyways, do you have any question about things to do? Everything's rather good. Go ahead.
So for C3,
C3.
how did you get access to the software that you're using? Because I tried to get access to
C3.
it, and it was telling me Adobe wasn't working.
C3, do you need a software?
Well, you demonstrated in
Yeah.
the lecture.
JavaScript?
What?
JavaScript, yeah.
Yeah.
Do you want to use it?
I mean, I would like to understand what you were doing in the
Okay.
lecture. But
Yeah, JavaScript, it's kind of finicky, but you go to Virginia Tech Java ENG upgrades. This is the page, and then here's ideal flow machine I've been using,
okay.
demonstrating in class. So just click on and run it. I hope it runs.
That's where I got.
Oh, actually, it doesn't run. Okay.
Yeah, that's where I was at.
Yeah. So now you have to go through all of those security programs. You know, go to. Do I even have a Java? I don't have a Java. I have to install Java. You have to go over the security, register the website, and only then you can run it. Because people do all sorts of bad stuff these days for JavaScript. So if you want to run Java, please let me know. I give you instruction sheet of paper. Okay. I don't think you need to run it though. It's just demonstration I showed you.
Yeah, it was a nice follow along.
That's right. Yeah. So this is the JavaScript, which is the both expand method. This is very bare bones, fundamental, something I was involved. And then this is essentially X-Player 5. It's essentially for the expand method code. Yeah. So nowadays, I don't feel like you have to run this code, but if you want to run it, let me know. You have to follow through exactly step-by-step process to know what the security of Java, so that you open up the security hole for your machine purposefully to run. If you feel uncomfortable, don't do that. Okay, but I'll let you do it. Please let me know if you want to run it. I don't think you need to run it though. Any other question? Yeah, those are just a bunch of Java projects under the National Science Foundation NSF project when I was a graduate student. When I was a graduate student, like what, 20 plus years ago. Who was the professor? Davenport, right? Where's the homepage anyways? Yeah, yeah, William J. Davenport, Professor Davenport. He's Scottish. Half of the time I couldn't understand what he was talking about. Anyways, any other question? Working all days at the version attack. Okay, updates. That's good. Updates. Okay. Oh, there's nothing new updates. You just do things. That's it. Okay. Any questions? Next item is project to be due Friday noon, and then did you? Oh, by the way, did you make your team project 3?
Some of us have.
Yeah. Well, it's free to sign up. If you just sign up with the same people, that's fine. It's easy if you want to do that. Okay. But again, it's open, so please sign up and make up your own team. I'm going to probably double check at the beginning of Friday's class. If some of you are not signed up yet, I'm going to sign you in on Friday. Okay? You don't have to wait for me. If you form up your project team or project 3, you just get it done. Especially 3A is just a summary report of how to use the software, so it's easy. Go ahead.
When are you gonna have 2A graded?
I don't know. I do my best. When do you need it?
I was just wondering.
I just do it as soon as possible. Yeah. Go ahead. Question.
For 3A, so we're to watch those YouTube videos and sort of understand how to use XFLR5.
Yeah. And
Um,
also materials given too, right? Here is like unit D3 notes. This actually gives you a demonstration of how to get started, and then do some very fundamental 2D analysis. Based on that, you can actually open up in 3D design.
Okay.
Step-by-step process.
Okay.
Yeah.
I feel like we could write a lot more. I feel like there's some time constraints. So like, what
Yeah,
is-
that's fine. I guess this is 3A is your team's common property, which is the summary or memos how to use this particular software.
Okay.
In other words, something useful information that you can share within your team.
Okay.
It could be crappy, I don't know. If so, I mean, I give you a score anyways. But if you make a crappy document, I guess it just doesn't serve it. Doesn't meet the purpose. I guess you can continuously build your own memo summary document.
Okay.
Yeah. Go ahead.
I was just gonna ask. It might sound dumb, but like,
Don't try if it sounds dumb. Anyway, go ahead.
it's just like bullet points. Like
Bullet-
for the memo, can it just be bullet points?
Yeah, sure.
Okay. So
I mean,
just list of
it
like
doesn't
things.
sound like dumb at all. Bullet points, great idea. That's engineers documentation. Engineers
sarcasm.
always use bullet points. That's
Why
fine.
don't you use the word, but-
It is, yeah.
That's great. You know, I mean, nothing wrong with that.
3A.
Any other questions? Let's get into Unit C2, high-speed error. High speed. High speed means more than 0.3. And then I touch a little bit basics of supersonic, but supersonic is essentially the subject of error 2. Because supersonic speed, basically at that point, physics kind of changes, and then you start ignoring the viscosity. Because supersonic speed, almost all the drag comes from formation shockwave. So if you understand what kind of shockwave is formed up, almost all the drags comes from there. So your design purpose is going to be completely different. Physics changes for high-speed airplanes. So that's why high-speed airplanes, especially supersonic type of airplane, looks completely different. Okay. So today we're going to cover high end of subsonic. It's not supersonic. So compressibility effects gets in if you start flying more than 0.3. This is the key. More than 0.3 Mach number is still subsonic speed. However, you have to keep in mind that the density is a variable. Density will be another variable. You have to keep track of it. So this one continues like less than 1. So still subsonic. This is called, okay, it's a important word. What am I talking about? This is like introduction to transonic aerodynamics. Transonics. Okay. So transonics is highly nonlinear behavior, so there's no way you can explain transonic aerodynamics using theory. So lots of discussion here depends heavily on past experiences and experiments, data, other things. Okay. Transonic aerodynamics, just introduction to it. I hope Aero 2 covers a little bit more. Okay. So this is just introduction to compressibility effects. So first of all, let's just properly understand, we talked about in last class, CP distribution. Do you remember this is CP distribution? Do you know the equation for that?
Isn't it the sign? It's gonna be.
Oh, that's if it's a flow over agenda, yes, but this is a flow over cross section with wind. What is the equation for that? Go ahead. Go ahead.
Is it 1 minus v over v?
Oh, that's right. So 1 minus
That one.
velocity distribution divided by free stream velocity squared. It's going to plot you this shape. That means this is not the CP distribution over the surface. As a matter of fact, this is the velocity distribution over the surface. This is, we're going to call this CP0. Okay. So this is a CP distribution for low speed. That means if the flow is low speed, what is the governing equation?
Kuczkowski? No.
Governing equation that actually relates the velocity and pressure. What kind of equation do you know from this class? Your knowledge supposed to be questioned in job interview. People ask you this kind of question. Go ahead. What is the governing equation of this CP0 equation here? Bernoulli's. Yes. Bernoulli's basically says that the density is a constant. You are less than 0.3 Mach number. Here, this is the low speed, right? Density is constant. That's the basic assumption of Bernoulli. If so, velocity and pressure are correlated. That's called CP0. In other words, you are going to keep track of the pressure change over the surface. At the same time, you keep track of the velocity change over the surface. That means lowest pressure point is the highest velocity point. At the same time, highest pressure point is the lowest velocity. As a matter of fact, CP1 means 0 velocity. This is stagnation point. You can tell those things, right, by looking at CP plot. This is called CP0. Okay. So this is entirely based on Bernoulli. This is velocity 0. This is velocity, what is 0? Okay. Velocity 0 point, stagnation point. This is the, velocity is maximum. Minimum pressure point, P min. Huh? Static port is right here. CP is 0. If you make a drill hole right here, it's called static port. Yes. Pressure is equal to the atmospheric pressure at that point.
So
you can tell two information at the same time, velocity and pressure, because those are correlated. Velocity pressure coupling. That's called Bernoulli's equation, low speed aerodynamics.
Okay.
Big picture, understand big picture, because people ask you that kind of big picture. If you don't understand big picture, you don't understand anything. Job interview is always a big question. Do you understand the basics? Oh, yes. So that's my emphasis. So that's CP0, okay? Now, what happens if you go for higher speed? That means more than 0.3. Still subsonic, but, wow, wait a minute. Density is no longer constant. So this is the CP0 you've been talking about. So this CP0 is a CP distribution over the surface, assuming that density is constant. However, your airplane is now flying more than 0.3 Mach number. Density is no longer constant. You have to correct it, right? Correct your CP distribution every time when you measure the CP distribution over the surface for a given condition and angle of attack. You have to correct it because you're flying more than 0.3 Mach number. This is a correction equation, Crandall-Glover. Okay, so this is the actual CP. If this Mach number is more than 0.3, you have to correct it. In X prime 5, do you have this kind of option, special team? Did you find this kind of special option of X prime 5, Mach number more than 0.3? You just check mark it and turn on Prandtl-Grawat equation. Did you realize it? You have to turn in Mach number, right? If Mach number is keeping 0, it's CP 0. But if you plug in Mach number, I don't know, 0.7, you turn in Mach number 0.7 here, all of a sudden you activate this equation. Okay? Go ahead.
And CP0 is the 1 minus V over V infinity.
That's what I said, yeah, that's Bernoulli's equation. Okay, this thing. Okay? All right, so now you have to turn on or activate this equation in your X prime 5 software. And then it does basically using this equation to correct your CP, okay? Because CP 0 can be computed by surface velocity distribution of a panel. But since you're flying more than 0.3 Mach number, those computed CP 0 need to be corrected based on Prandtl-Grawat. This is called Prandtl-Grawat rule, okay? Here we go. But this is just an estimate. Estimate means, hey, this equation comes from past data and then data fit. This is not based on the theory. So suppose if you want to stick with the theory, what kind of theory is available for more than 0.3 Mach number instead of using Bernoulli? What kind of equation do you use? Energy equation. There we go. So one of the homework assignments unit of this unit C2, I force you to correct CP in 2 ways. One, using Prandtl-Grawat. The other one, directly apply energy equation to do the exact same CP calculation. Instead of using Bernoulli, you go ahead and use energy equation version of Bernoulli's equation for CP computation. Can you do that? Yes, you can. Okay. Where do you go back and take a look at it? Which unit?
A5.
A5, yes, correct. Oh, you're good, Robert. Your response is so good today. I don't know why. Well, I shouldn't say that. I'm sorry. Okay, don't take it personally. Your response is good. Let's stop there. Okay. So, my goodness. Okay, so let's talk about critical Mach number today, MCR. Okay. So concept of critical Mach number is the following, okay? So this is the choice of your airfoil, cross-section of a wing. This is your flight Mach number. Your airplane is flying 0.3 Mach number, okay? Now, this 0.3 Mach number flow gets in, maybe hit stagnation point. Maybe some of them flow over the surface and accelerate and flow away. This is the most accelerated point. Pressure minimum here. Mach number is optimum. That means flow here is accelerated to 0.435, even though your airplane itself is flying 0.3 Mach number. Does it make sense? Portion of the surface of your wing is actually accelerated more than you are flying your airplane. Now, if you continue accelerating, now you are hitting 0.5 right here, and minimum pressure point or peak value of Mach number becomes 0.772. Now, you continuously accelerate, and then here, this is the critical situation. Now, this peak point where the pressure is minimum, now you have Mach number 1, sonic speed. Even though you are still flying 0.61 Mach number. Here we go. This is called critical Mach number, MCR. That means 0.61 is a critical Mach number. What does that mean? This is the Mach number where minimum pressure point on the wing now becomes the sonic speed. If you accelerate more than this, what happens?
Supersonic.
You are going to develop supersonic region over your wing. That is going to cause lots of issues. That's the transonics. Shockwaves, yes. That's right. Oh my goodness. have you ever seen, taking your airplane, go back to your hometown, take a look at wing, and have you ever seen shockwave? Oh, look at that, that's shockwave forming. Probably not. Because if you're forming shockwave, your airplane is going to be not going to fly right. You can sleep.
There are videos that you can see where it ripples a little bit right in front of the leading edge, even on commuter flights. But it's very, very small.
That's probably just a structural vibration. Probably. Because shockwave is so violent, okay? It's going to be violent.
Yeah.
It might destroy the structure. And then supersonic airplanes, do they have this kind of wing? No.
Thin plates.
If you have this kind of wing, those sections will be cut off and fall off because shockwave is created from the nose with some angle. And then if that shockwave hits your wing, that wing does not survive. It is going to be permanently damaged. That's why this is this. Have you ever seen this airplane right next to the building? Well, there's a reason why. I mean, this is the only wing you can afford. Okay, anyways. So, yeah. So this is the critical Mach number. This is a design parameter. Every time when you design your airplane and then claim that airplane is a high-speed airplane, number one question that people ask you is, what is your critical Mach number then? Tell me about it. Design parameter. If I'm sitting next to, if I'm sitting as a panel, and then if you are senior student and then presenting, hey, this is a senior design project, this is a supersonic airplane, my first question is, give me critical Mach number. Oh, 0.5. Then I go like, give me a break, I'm gonna go home. What are you talking about? It's not the high-speed airplane at all. So this is actually a very important design parameter. So do you want to have a high value or low value? As high as possible. As high as humanly possible, that's the critical Mach number if you want a high-speed airplane. Go ahead.
Does reducing your wing camber increase your critical Mach number?
There are lots of design choices to increase critical Mach number. We're going to talk about it a little bit later. Yeah. But so this is the design parameter, critical Mach number. So let's spend some time today to find out what it is. How can we determine such a thing? Okay. So let's just take a look at next page. So in order to determine such a thing, okay, first of all, let's find out equation of critical Mach number. This is 30, that's why. So first of all, if you want to have higher value of critical Mach number, which one do you choose? Thick one, medium one, thin one? Which one is the best choice to have a higher critical Mach number? Thin one, yes. Why is that? Well, of course, flow is going over each one of those. Now, obviously, starting from the leading edge, flow accelerates, and then most likely very close to the leading edge, you're going to establish minimum pressure point or most accelerated location, which is critical point, right? Those are the critical points. So that's the critical point of CP. In other words, lowest possible value of CP for each different shape. Those are just example values. So if you choose thin airfoil, most likely the lowest possible CP is about range of minus 0.5-ish. But if you choose the thick one, it's already accelerated well enough. CP value is pretty low, minus 1.5 to begin with. Okay? Then those are the curves based on the Prandtl-Grawat. Do you remember Prandtl-Grawat? This is the equation. Basically, CP is equal to corrected by free stream Mach number. So CP0 over square root 1 minus m infinity squared. So this is the Prandtl-Grawat curve. Okay? And then each one of those values are CP zeros of each choice of type of cross-section of airfoil. So CP0 for thick airfoil is already pretty low to begin with. So that means thick airfoil actually accelerates, oftentimes accelerates too much. Okay? So that's why you don't want to accelerate if you want to design high-speed airplane. Because accelerating too much means that even though your airplane is flying still 0.6 or 0.7 Mach number, you already meet up the sonic speed at this minimum pressure point. It just simply accelerates too much. Okay? So we want to avoid it. So this curve is a Prandtl-Grauer curve. Prandtl-Grauer curve. And Prandtl-Grauer curve. Then you want to find out the other curve here. Okay. This curve represents curve of CP, CR. So this is called critical CP. Critical CP is a CP at critical point. Okay. Critical point is, of course, pressure minimum location. What is the CP at that point? This is actually a function of Mach number also. So you are going to plot Prandtl-Grauer and CP-CR plot, find out the crossing point for each different shape, and then find out what Mach number of free stream those two curves cross over. This is going to determine critical Mach number. So obviously, if you have a thick cross-section, critical Mach number tends to be lower value. If you have a thinner airfoil, critical Mach number tends to be higher value, of course. You choose this one for high-speed airplane. This is a choice. So let's just find out the equation of CP-CR as a function of free stream Mach number, okay? So let's just do that. So this is actually a pretty simple equation, okay? So we're going to start from here. Starting from the definition of CP. Anybody? Very original definition of CP. Oh, that's the
CP0 over the bird of 1 minus Mach number squared.
P minus P infinity over Q infinity. This is the original definition of CP. So let's just change the format a little bit. So this is P infinity over Q infinity. Change the format a little bit. P over P infinity minus 1. So I just changed the form a little bit. So this is the original definition of pressure coefficient. I'm going to call this equation 1. Okay. Also, Q infinity is dynamic pressure of free stream, rho B squared, 1/2 rho B squared. I'm going to also change this form a little bit. 1/2, okay, rho infinity divided by gamma times P infinity multiplied by gamma times P infinity B infinity squared. You can do that. Multiply divided by gamma times P infinity, which is 1/2. This is a B infinity square. This is going to be gamma P infinity divided by rho infinity multiplied by gamma P infinity. Okay, so far.
Really quick.
Yeah.
You have Q infinity is equal to 1/2 rho infinity B squared infinity, and then that's equal to 1/2. Is that rho infinity on top over gamma?
This
P
is rho infinity.
And then P
This is
infinity.
gamma P infinity multiplied divided by. You can do that.
Where did you get it?
Huh?
Where did you get? I know it came from like the Brazilians, I believe.
No, I mean, I just multiply by gamma P infinity divided by gamma P infinity. It just cancels out. I can pop up.
I guess.
Yeah.
Just make up-
Okay. Yeah, I can make up something because I have a purpose later. You're going to find out the purpose. So why am I doing this? Anyways, let's move on. Okay. Also recall free stream speed of sound. Let's take square. What's this?
Gamma R.
Gamma RT infinity. That's right. So this is, by the way, isn't this gamma times P infinity over rho infinity, isn't it?
Yep.
Note, of course, note. P equals rho RT. P infinity is equal to rho RT infinity. Right? You can say that, right? So now, Robert, I think you should probably realize, hey, this thing can be plugged in here.
Yeah.
Okay. So this is plug into one. Plug into equation 2. Then what happens? Equation 2 now becomes. That's right. So now equation 2 now becomes Q infinity. Free stream dynamic pressure is 1/2 B infinity squared over A infinity squared times gamma times P infinity, isn't it? What is that? Mach number squared.
Okay, that's what's up.
That's what I'm doing.
Because like you can also plug it into the gamma P infinity.
Where?
Like you can make it where A squared times P infinity, I mean rho infinity is equal to gamma. But
Yeah.
I guess you don't want to do that.
Yeah, because I want to
Cancel.
have this form. 1/2. Okay, 1/2. Okay, P infinity. Sorry, 1/2 gamma over 2 times P infinity times Mach number infinity squared. So this is something I wanted. So this is the expression of free stream dynamic pressure in terms of free stream Mach number and free stream static pressure. That's what I wanted to have for a moment. Okay, well, just to stay with me. So let's just think about, this is your airfoil. Okay, and then you have streamline. You have probably multiple streamlines. One of the streamline goes straight into the stagnation point, maybe, right here. So right here is a free stream infinity. This is a stagnation point, point 0. And then let's just consider this is a critical point. So this is, pressure is P here. Mach number is M here. That's a critical point. Okay? Now, right here, Mach number is M infinity. This is your flight Mach number, free stream. And pressure is P infinity. This is atmospheric pressure. Okay? Right here is a stagnation point. Stagnation point, what is M0? Anybody?
0.
0, of course. This is velocity 0. P0 is a total pressure right here, stagnation point. Okay? So having said that, do you remember the relationship between stagnation point to the free stream, stagnation point to this location, as a function of Mach number in between? Do you remember the relationship for those? I think this is going to bring you back to the old memory of this class. You know, maybe fairly beginning of the semester when we talked about airspeed measurement. Do you remember this equation?
Oh, yes.
Unfortunately.
Oh, this is the priceless, you know, because people actually ask you this kind of thing. So this is a relationship, okay, between stagnation point to the location, in this case, free stream, okay? But any location between stagnation point to any other location is a function of the Mach number of that location, okay? So this is coming from what? Energy equation, okay? So this is essentially coming from energy equation. Relationship of the pressure between stagnation point to the location that you know the Mach number on that location. Because stagnation point, Mach number is 0. Okay, so let's apply this equation. Next page, okay. So I'm going to apply that relationship between free stream to the stagnation point and stagnation point to this location, okay. So this is, okay, recall. From unit A4. This is essentially coming from energy relationship, energy equation. Okay, so between stagnation point, pressure P0 to the pressure at the critical point, okay, I'm applying this equation between here and here. Okay, stagnation point Mach number is 0. Right here, critical point Mach number is m. Okay. So now P0 over P is 1 plus gamma minus 1 over 2. Mach number at the critical point is m square to the power of gamma over gamma minus 1. Okay. This is between stagnation point and critical location. And also you can do the same thing. Let's call this equation 4. Okay. Also you can say between stagnation point to the free stream P0 over P infinity. So this is 1 plus gamma minus 1 over 2. Now this is m infinity square gamma over gamma minus 1. Is that correct? Okay, so this is equation 5. So this is between stagnation point and free stream. So I guess the question is, can we combine those two to have a pressure ratio between critical point to the free stream, P over P infinity? Can we combine those two? How?
Them together.
Yeah, multiply by flip-flop of the other, right?
Yeah.
P over P0, flip-flop of equation 4, multiply by equation 5, P0, P infinity. Right? We can do that. In other words, you can cancel out P0, P0. Now you have equation something like this. So this is 1 plus gamma minus 1 over 2 m infinity square 1 plus gamma minus 1 over 2 m square okay to the power of gamma over gamma minus 1. So let's say this is equation 6. Now what? Now what?
You can plug it back
Into the equation 1, right? Look at that. So now what? You can plug in equation 6 in here. Equation 6 comes in here. So now, let's recall equation 1 all the way from the previous page. Let's just plug in equation 6 into equation 1. Plug in 6 into equation 1. You can say Cp is equal to P infinity over Q infinity. Also, 6 also Q infinity, we have another equation. Q infinity, yeah, Q infinity is this equation, equation 3, right? So you also need to plug in, sorry about that. So this Q infinity is equation 3 right here. Okay? So take a look at equation 1. You plug in P over P infinity from equation 6, Q infinity from equation 3. You just plug in those back into equation 1. Okay? Let's do that. Plug in 6 and 3 into equation 1. Okay? So equation 1 says Cp equal to P infinity over Q infinity, P over P infinity minus 1. This is equation 1. Okay, now of course, this is equation 6. This is equation 3. Let's just plug in both. What do you have? What do you have? This is big equation. P infinity over gamma over 2 p infinity Mach number infinity square bracket. Okay, 1 plus gamma minus 1 over 2 m infinity square 1 plus gamma minus 1 over 2 m square. Power of gamma over gamma minus 1 subtract 1. Here we go. So, what am I doing? What is CP critical? CP critical means that CP when Mach number equal to 1, isn't it? So let m equal to 1. Yes. So now you have CP critical question. CP critical is, let me just let m equal to 1 here and then simplify. Go ahead.
One quick question. You said that CP critical means that CP is when the Mach number is equal to 1. That's Mach number is equal to 1 at the critical point, correct?
That's right.
Okay, got it. Thank you.
Let me just add, that's a nice comment, at critical point. Because that's the minimum pressure point over the surface. That's the most accelerated location on the wing. Critical point. Go ahead.
So when you do P over P naught times P naught of P infinity,
Yeah.
is that just same thing as dividing them?
Huh?
Like where you have the two P naughts canceled out,
Yeah.
that's just dividing them out? Like, what is that?
Whoa. Okay. This is P, okay. P over P0 is inverse of that, so this is it, right?
Oh, okay.
P0 over P infinity is this. That's this.
Oh, I see.
Okay.
Yeah.
All right. Then by doing so, P0 cancels out, so you can now get pressure ratio between critical point pressure to the free stream pressure. Okay. And then that one you can plug in here. Okay. All right. So CP critical is once you plug in m equal to 1 and simplify, this is the equation you're going to get. Okay. Last final equation 2 over gamma m infinity square bracket. Okay, 2 plus gamma minus 1 m infinity square gamma plus 1 bracket another bracket to the power of gamma over gamma minus 1 subtract 1 cross bracket. So this is the equation of CPCR. Okay? So what do? Use this equation to plot out here. So this is the equation. So this is the CPCR equation. So this is a CP at the critical point, which is most accelerated location over the wing. Okay? Then this is the Prandtl-Gravert equation, starting from CP0. Then find out the crossing point. That is your critical Mach number. So this is a classic technique to determine critical Mach number. Whenever you design a high-speed airplane, you have to do this and then present your results of critical Mach number so that you can claim this is designed for high-speed use. If this critical Mach number is pretty low value, you're not going to convince anybody. Go ahead.
How high of a critical Mach number
Critical Mach number can be as high as close to 0.8.
to be considered high speed or?
Yeah.
Okay.
Again, P51D Mustang has a critical Mach number 0.76, which is pretty darn good. So that means, technically speaking, if you remove that propeller engine and, replace it with a jet engine, that could be pretty good high-speed airplane. Anyways, go ahead.
Would like basically as the cross section, as that becomes basically a line, is that when your critical Mach number approaches 1? If you just have the critical airfoil theory.
Critical airfoil. So
or not thin airfoil theory.
Thin airfoil. So.
So the thinner it gets, is that the closer it gets to 1?
Closer gets to 1. What do you mean? One is what?
As
Mach
your-
number one?
Yeah, your critical Mach number. As
Critical
your-
Mach number cannot be one.
Okay. So what's the highest we could possibly?
If it's completely flat plate,
That's what I was saying.
if it's completely flat plate with a zero angle of attack, it's not airplane because you're not going to create the rift. But if it's a completely flat plate for high speed, it is going to probably induce instant separation at the leading edge. It's not very good design anyway. The flat plate is. Yeah, especially high speed.
I was just thinking like theoretically. But...
Theoretically, you mean thin airfoil theory? Thin airfoil theory is limited only for potential flow. High speed is not that easy because the physics is more complicated, right? Now, in order to actually analyze high speed, you have to know the energy equation. That means you need to have a complete total information of temperature distribution. That is energy equation, right? That is not easy, okay, under any condition. Okay. That's why energy equation could possibly be theoretically sound, but is it useful? Probably not, most of the time. Okay. Now, completely flat plate is a different story, but it doesn't create the rift, right? Unless you create some camber. So here we go. That's actually an important thing. Probably the very beginning of the development of high speed is thin flat plate bent. That's probably the beginning. Yeah. So that's actually not so bad idea. But completely flat means you're not going to create any rift unless you pitch up. Once you pitch up a little bit, you induce the separation, right? That's not very good. But bent a little bit of camber, no thickness, that could be ended up your design choice of your senior design project, and people rough at it, but it's going to be a best choice kind of. I don't know. Who knows? Okay, go ahead. Okay. Any question?
Yes. My question is, so
Yeah.
you plugged in one.
Plug in one here,
Yeah, so did
and
you
then finish
do-
up your mass.
Yeah, did
I
you-
don't want to do mass. Finish up your mass. Plug in one here. This equation becomes this.
Okay.
You can simplify, okay?
Yeah.
So any other question? Let's move on. So next thing is, so we're talking about critical Mach number here. Okay. So critical Mach number is, okay, obviously, you are still flying subsonically at the minimum pressure point, critical point. You're going to experience sonic speed. And then if you go beyond that, what happens is drag coefficient starts to increase rapidly. This is called drag divergence, something called MDD. Drag divergence mechanism is the following, okay? If you go beyond the critical Mach number, what happens is you're going to start developing supersonic region, at least partially, over the surface, okay? Now this one, creating typically normal shock wave burn to adjust the supersonic into subsonic flow. So this normal shock wave actually separates everything behind it. This is called shock wave induced flow separation. So entire surface behind shock wave flow is all separated. It's a terrible flight. It actually happened to X1, okay? Every time when X1 tried to approach the sonic speed, this happened all the time. This actually induced two things. One is a skyrocket increase of drag coefficient. The other one is loss of rift. Oh my goodness, because flow is not attached. So you lose your rift, drag increase. That's called drag divergence. And then classic definition of that is shock-induced flow separation. And then 1950s and 60s, NASA engineers called this sonic barrier. Oh, because we cannot break the speed of sound. And then nowadays we do know how to deal with it, okay? So this is one such a solution, supercritical airfoil. Okay, so supercritical airfoil, by the design, you are going to avoid acceleration on top surface. Do you know what I'm talking about? So this is a conventional airfoil. Flow really accelerates established minimum pressure point right here. Now, if you make the top surface almost completely flat, that means you're not gonna accelerate the flow on top surface. That means, take a look at that. Most of the top surface flow is not accelerated, you're going to avoid creating minimum pressure point right here. So you can actually avoid forming the shock wave. Okay, so this is supercritical airfoil. Almost all transonic airplanes cross section today is supercritical airfoil. So this is very fast application of it. This is the C-17 Globemaster 3. This is patented by McDonnell Douglas. This is airplane right now. Brian, go ahead.
If you, I guess looking at the cross section, it almost looks like an upside down airfoil. Does it still
Upside down
produce?
airfoil, not quite. Actually, top surface is intentionally making it flat, but the bottom side is curved out so that creating intentionally higher pressure zone on the bottom side, so that most of the lift is supported from the bottom side toward the tail. So this is after rolling airplane. So conventional airplane actually create low pressure on top side, so you pull up the airplane, right? So this one is actually creating a higher pressure zone on the bottom. So airplane is lifted up from the bottom. So it's like a, yeah, you're basically saying that it's a completely flip-flop idea of how to create the wave, right?
So having these supercritical regions where Mach is greater than 1
Yeah.
forms a shock, that's okay as long as the shock wave is at the very end of the body.
Usually, yeah, usually this formation of shock wave is completely avoided. Completely. You're not going to create any shock wave. Right.
Do these airfoils make the same or comparable amounts of lift to conventional airfoils, or do you have to be going a lot faster?
I guess so. If you take a look at the area, because this area is essentially lift coefficient, right? So I guess the question is about the same area you created, but which portion? Is it the high pressure zone or low pressure zone more contribute to the area? So again, amount of lift, it depends only on the area that you produce. It's about the same, right? Yeah. So now, oops, we couldn't finish up Unit C2, but on Friday, okay, we're going to finish up Unit C2. But take a look at the high speed. This is actually supersonic. Okay. So on Friday, we are going to take a look at supersonic, just the introduction to it. And then we're going to get into Unit D1, which is a 3D wing, okay, on Friday. All right. Have a good day, and see you guys back on Friday.
Yeah.